that I say, my stupid drawing, you'll hear me drawing on about stupid stories. You're going to hate part of this lesson. It requires algebra that you don't like. I know you don't like it. Well, graphing isn't going to be a huge part of this. I'm going to show you how to solve this with graphing, but graphing is not the best way to solve these. Because if you end up at a solution that is fractions, you're never going to be able to graph it so that you can see which fractions are coming together. So this is the only one I'm going to show you how to graph. And then I have to show you how to solve it algebraically. And then I have to explain one of the methods algebraically. You're going to hate that one because I just came up with it. And then after that, it's all algebra. And it's not really hard stuff. You just have to focus on what you're doing. Most people are very good with this. Most people are very good. All right, so if I want to find the intersection of these two lines, I'm going to graph them. And I gave you all graph paper. So my graph is not going to look as good as your graphs are going to look.
Close the door.
Everybody's here.
Everybody's not
I'm just curious. I used to have rulers in here. I don't see any. So you'll be able to sketch this a little bit better than I do. So if I want to graph these two lines, what do I do first? Solve for y. To get it in y equals mx plus b form. So if I solve for y in this one, you're going to get 2y is equal to negative 3x plus 6. I like keeping the x first because that's where the slope's going to come from. And then divide everybody by 2. And you get y equals negative 3 halves x plus 3.
You just shut the door.
And I said everybody was here. I'm like, oops. That one. All right, solve the other one for y. Negative 4y is equal to negative x plus 16. This would be to the other side. You should be experts at linear solving nowadays. All right. Divide everything by a negative 4 and you get y equals
1/4x.
1/4 x minus
12.
subtracting.
Sorry.
16 divided by negative 4 is negative 4. All right, so how would you graph these two? What's the slope over here? Negative 3 over 2. Y-intercept is?
3. Negative
0, 3. Thank you. So the slope, change in y over change in x, and the first one is negative 3 halves. I like this notation better than just n. N doesn't tell you anything. And the y-intercept is 0, 3. All right. The slope over here, change in y over change in x, is equal to 1/4. And the y-intercept is
0,
negative 4. Okay. So that's the second line. Line 1, line 2. Now, graph paper time. Let's see if I can draw this decently enough. That's not too bad.
It's actually straight.
Is it?
It looks straight.
It looks straight to me. Alright. 1, 2, 3, 4, 5.
Yes, I already got
1,
it.
2, 3, 4, 5. I said you're going to have it easy because you have graph paper. 3, 4, 5. The problem by drawing it like this is your tick marks could fluctuate in size, and that distorts your graph horribly. Graph paper is much more easy because it's already evenly spaced out. 1, 2, 3, 4, 5. All right, so I'll plot the two lines in two different colors. We'll go green and red, black, whatever it is. It depends on what it shows up on. So the first one has a y-intercept of 0, 3. So 0, 3 is here. The slope is negative 3 halves, so where do I go?
It's 1 down 3
Down 3
over 2
and right 2. So we would go down 3, right 2, and if I want, I can go down 3 again. 1, 2, 3, and right another 2. I like having 3 points. Makes it easier to draw my line, especially up here on the board. All right, so this would be the first line. Let's see if I can draw it nicely. Close, no cigar. That's all right. Make my point really big so it touches the line. So down 3, right 2, down 3, right 2, and draw a line through those 3 points. All right, the next one we are going to start at 0, -4, which is down here. It's black on my marker, but it's red on the screen. From 0, -4, what do I do?
Go up one.
Up 1
Over.
and over 4. 1, 2, 3, 4. Which lands right on top of
Third point.
one of the slope points of the other line. So this line is going this way. Oops. It should lie right on top of it. Down 3, right 2, this point should be here. It's down here. You went down 2 over 2. Should be down 3 over 2. So this here becomes the point of intersection. What is the coordinate of that point?
4, 3.
It's 4 to the right and 3 down. So this point 4, 3 becomes known as the solution to the system. So,
Would it be 4 -3?
ooh, you're right. Who said 4, 3?
I'm sorry.
4, -3, down 3. So when we write this as a system, it gets a fancy little racy like that. The first equation was 3x plus 2y is equal to 6. The second equation was x minus 4y is equal to 16. And the solution is the point for -3.
It's a hard pen.
It is.
It's what?
Hard.
Hard? Oh, I gotta press hard so it,
Transfer.
if I do it soft, it might not click the sound part of it. All right, so one way of knowing it's a solution is, yeah, the 2 lines cross and they hit at these 2 points. What if I feel like I graphed them wrong? Well, I can check it. How would I check my work?
Go back and plug in.
Yeah, this one is x, this one is y, and plug it in. So x is 4, so 3 times 4?
12.
We're here. So you got 12, and then 2 times -3?
-6.
And 12 minus 6 is?
6.
6 comes out to the other side. If I plug in 4 to the bottom one down here, you're going to get 4, and -3 times 4 is positive 12, and 4 plus 12 is?
16.
And it checks out. So it's kind of cool if you think about it. So any other point you choose in the plane, I don't care where it is not going to be a solution, because if I choose even this point on this line and plug it in, it'll work for one of them. It'll work for the green line, but it won't work for the other one. It has to work for both. So that's the essence of solving a system of equations. It is technically where 2 lines intersect. Now, do all lines intersect?
No.
No. What are the other possibilities then?
Parallel.
Parallel. Now, if I have 2 lines that are parallel, and they share no common points forever and ever, what solution do I get?
Infinity.
None. I get none, so my solution would be the empty set. There is no solution because there are no points of intersection. The other possibility is a little stranger. You could have a line going in that direction, and you can have another line right on top of that line. So I'm going to kind of...
Oh, that line.
So they're exactly the same line. How many solutions would you have?
Infinity.
You'd have infinite number of solutions. Any point you choose on that line is a solution to the system. Now, are those 2 systems interesting?
Yeah.
No. They're boring. No solution. Every point on the line is a solution. Now, be careful. This point over here, if you're off to this side, is not a solution to that system because it's not on the line. But once you're on the line, it's an infinite number of points that are solutions. But those are too boring. None at all. So I'd rather prefer having a nice singular solution. So most of mine lean in that direction. There's fancy names for the other 2, but I usually don't run into them. Okay. So what's the algebraic way of solving these things? And I'll do it with the same setup, and we already know what the answer is for -3. That came out horrible. I always have a problem with that side of the board. I don't know why. Alright, so I have to be careful.
This is so cool.
This is so cool. Method 1. if we have this system, 3x plus 2y is equal to 6, and x minus 4y is equal to 16, method 1, we're going to call it substitution. Substitution. And this method is pretty simple. You pick one of the equations. I'll write it down here. Pick one equation. Once you pick that one equation, solve for one variable. I could care less if you solve for x or if you solve for y. Pick one of them. I don't care which. Then, when you're done with the first equation, 3, plug into other equation. And then 4, of course, solve. That's pretty much the essence of it. So you're going to pick one of these two equations, solve for one of the variables. Once you solve for one of those variables, you're going to plug it into the other equation. Don't plug it into the same equation, because you'll end up with a line on top of itself. That type of situation. All right, so which equation do you want to pick? Top or bottom?
X minus 4y.
X minus 4y. Which variable? Solve for x. It's the easiest one to solve for. Don't go for the hard ones, go for the easy ones. So I'm going to solve for this x in the second equation. So I get x is equal to 4y plus 16. Now, once you're done solving for the variable in this equation, ignore that equation completely for a little while. Go back to the other equation and plug this in.
3, 4y.
So 3, you're substituting in for x, plus 2y is equal to 6. So it's 3 times something plus 2y equals 6. That something happens to be
4y plus 16.
4y plus 16. And now you have an equation which the only variable is y. We can solve that. So how do you solve? Distribute 12y plus 48 plus 2y is equal to 6. Then what?
Add your
Like terms. So you get 14y plus 48 is equal to 6. 14y is equal to negative 42. And then divide both sides by 14. And you get y is equal to,
3.
It's just
and if you go back to our solution over there, y was equal to negative 3. So this would be an algebraic way of finding that point of intersection. All right, so how do I find x? Where would you plug it in? You could go all the way to the top.
Or you can do the
Or you can go to where you have x already solved for. If you trust us enough. So if you know you did this one perfectly fine, take a y, go back and plug it in there. So then you get x is equal to 4 times negative 3 plus 16,
you get
which is negative 12 plus 16, which is 4. And therefore, my solution is x equals 4, comma, y equals negative 3.
so instead of doing the graph way, you can do it also that way, right?
Right. The graph way is awesome if it lands on integers.
Okay.
But once it lands on a fraction, graphing is useless.
Right.
Unless you break up your graph paper into lots and lots of little pieces, but most people wouldn't do that. So the algebraic way is much, much better. Not hard, right?
Why is it the end?
Where what?
Like chapter 5.
It's the end.
I'm saying like it's more simpler than what we've been doing.
Oh, isn't that funny? It gets worse.
Okay.
Oh, you thought it would just be this easy all the time?
The first section always easy.
No, this gets worse. How about this one? I mean, technically the algebra doesn't get horrible. But sometimes when you do this method, the numbers aren't nice. So here, the numbers aren't nice. They're horrible. But we're going to drudge through it and see what we get. So if I'm going to do this with substitution method,
Somebody had to do it.
I have to pick one of those two equations and solve for one of the variables and plug it into the other equation. That's all there is to it.
Is it negative 43?
It's negative 43. So which equation do you want to pick?
Top one.
Top one. Which variable do you want to solve for?
Why?
I highly suggest it. It's the only one that it goes into the other side. So I'm going to solve for this y right here in the top equation. So that becomes 4y is equal to, now order doesn't matter. You can write it as negative 3x plus 16 or 16 minus 3x. Me personally,
And this.
16 minus 3x. I like that minus sign in the middle. That way I don't lose track of it.
So you don't make your 16 negative? Oh, no, because you know.
Yeah, I'm just subtracting the 3x over. I'm not interested in slope and intercept here. I just care less about that. Then go through and divide by 4, so you're going to get y is equal to
4 times
3/4 x. The minus sign in between, it gets trapped, and therefore you can't lose it. I've seen you leave negatives before, all of you. You know, that negative in front that just magically disappears. So it's better to hide it in between two numbers, then you don't lose it usually. All right, what do I do with this?
Put it in the other equation.
Plug it into the other equation, the one you didn't touch to begin with. So this is going to become, what am I substituting into? The y, so it becomes 2x minus 5 times something is equal to negative 43. What do most people make a mistake here on? That other number on the other side. They get so concentrating on what goes next to the 5 that the other number gets
Left out.
messed up or left out completely. Yeah, I've seen that too. Inside here goes 4 minus 3/4x. Ooh, guess what we're going to end up with?
Fraction.
Woohoo! I love fractions. All right, distribute. You get 2x minus 20.
Huh?
Oh. 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 2x minus 20 plus 15/4 x is equal to that w negative 43 on the other side. Now,
Combine like term.
good luck. All right, 2x plus 15/4 x. Or I could use another trick that I taught you at the beginning of the year.
Well, it's multiply both sides.
By
4.
4. You could if you wanted to. But hopefully I think you can get this as 8/4, and 8/4 plus 15/4 is 23/4.
Yes.
Right? So this becomes 23/4 x minus 20 is equal to negative 43. But if you don't like the fractions, multiply everybody by 4.
Add 20.
Add 20 across, you get 23/4 x is equal to negative 23 after you add 20. Now what?
Divide.
Well, divide by 23/4. But that's the same thing as multiplying by
4 over 23.
4 over 23. So I'm going to multiply both sides by 4 over 23. The 23s will cancel, the 4s will cancel. Perfect. So 4 over 23. When we started this, did you think we'd get a nice answer?
No.
No. But this is actually quite
Nice.
nice. What's the answer?
Negative 4.
Negative 4. So x equals negative 4. And once you get x equals negative 4, game's over. The last step is simple.
Plug it in.
Go back in. I'd highly suggest plug it in here or either of the two original equations. So we're going to get y equals 4 minus 3/4 of negative 4. So y equals
7.
7. So the solution to the system, just to emphasize it, is
Negative 4, 7.
negative 4 for x, positive 7 for y. It is a coordinate on a piece of graph paper where the two lines are actually intersecting. Okay. Pretty cool, huh? Great. Is it the best way of solving a system of equations? Sometimes not. Sometimes the fractions don't ever go away. You'll get fractions like, huh?
Is it the what way?
It's the best way to do it all the time.
You said the bestest.
Bestest way, fine. Whatever. English language isn't my first language. Math was. So, the best way. with substitution is sometimes the only way to do systems. And systems are not necessarily linear. They could be circles, parabolas, a lot of other weird things intersecting each other. So sometimes it's the only way to do things. Solve for one variable, shove it into the other equation. But linear-wise, we might have ended up with x equals negative 23 over 81. And then we would have to substitute that into, and it just gets
Weird.
fraction intense. It sometimes gets a little messy. So I want to come up with a method where we don't have to worry about the fractions until the end. And that method, the book doesn't explain why it works, so I'd like to explain why it works. You're not going to like the explanation, but I hate using things that I don't know why they're working. You know, I start doing this process and I'm getting answers, but I have no clue why it's giving me the right answers. I hate that. So this is where it's going to get messy. Because I did it earlier to make sure my brain was working right. And it becomes quite messy. So the essence of the method that we're going to be doing, method 2, this one is called addition by the book. I call it elimination. It's much more descriptive of what you really wanted to do. You wanted to get rid of stuff. So let's look at this first word, addition. We're going to take two equations and literally add them together. And this is where it gets confusing. You're taking two lines and you're just adding them together.
Isn't it how we did it in like high school or something like that?
Uh-huh.
Oh.
But now I have to explain why it works, because nobody ever explains why it works. They just go, oh, just do this and you get the solution, but then they never say
How you got
why. So when I write my equations of lines, I'm going to write it this way. That's an equation of a line, right? Okay. And M1 would represent a slope. X1, Y1 represents
The coordinate.
a coordinate that it actually goes through. So my whole purpose of solving the system of equations is where two lines share a common point. So what I'm going to do is I'm going to set this up that the solution is x1, y1. The solution to my system is x1, y1. Okay, so that's one equation of one line. Here's another equation. Has a different slope, but it still goes through the point x1, y1. So far, so good? Okay. And what I want to do is I want to add them together and see what happens. So if I take these two lines and I add them together, left side to left side, right side to right side. It's a little weird. You've never done this before, but it works. When I add these two together, they're exactly the same. So I'm going to get 2y minus y1. Now the fun starts. What do I get on the other side when I add the M1 thing and the M2 thing, which is exactly the same, by the way? What do you think you get? Nope. Well, you could actually consider it M3, but I want a little bit more precise. You're going to get M1 plus M2 times
X1 minus X1.
X minus
I mean,
X1.
X minus X1.
Yeah. It's the same thing as if you had AX plus BX. You would keep the X's and go A plus B, right? So this becomes M1 plus M2 times X minus X1. Well, that's just a line. It's another line. I can actually write it y minus y1 equals M1 plus M2 divided by 2 times X minus X1. Where does this line go? It has its own unique slope. Hey, by the way, what's the slope? What do we call this when we add two numbers together and divide by 2?
The mid.
The average.
Oh, yeah.
Yeah, it's just the average. So this is the average of the slopes. What point does this line go through? Well, X1 and Y1. So these three lines are actually going through the same intercept, the same intercept. So if I was going to graph this situation, here would be, a line with slope M1. And here would be a line with slope M2. And this point of intersection that I'm interested in is x1, y1. So far, so good. All right. And what I just created was the average of these two slopes still going through x1, y1. So this would be another line that actually just goes through it. This is the one I created. We can call this M3 if you want. The average of the two slopes, like you wanted to call it M3. But it still goes through that point of intersection, that one I'm interested in. So here's the goal. This blue line is just another line in x and y. I can make it any line that I want. I can adjust these two to force the sum of it to be a little bit different. In other words, I could take the top one and multiply it by 2. Does it change the line?
No.
No. And if you have y is equal to 2x minus 4, then I multiply by 3 and I get 3y is equal to 6x minus 12, there is no difference between those two lines. So I can multiply by any number that I want. But after I add it together with another one, I can manipulate something. So it's just kind of a neat method. But the idea is, whenever I add two of these lines together, I get another line that goes through the same point of intersection. Guaranteed without a doubt, if it has a point of intersection. All right, so let's do a simple one. Here's a simple system. I can even give words to it. The difference of two numbers is 7. The sum of these two numbers is 15. What are the two numbers? The difference of two numbers is 7. The sum of two numbers is 15. What two numbers am I talking about? Well, let's do the addition method. I'm going to take these two equations and just add them. Let's see what happens. So, 2x,
They cancel out.
the y's cancel out, is equal to 22. Now remember, that line, 2x equals 22, is another line that goes right through that point. The beauty of it is, what kind of line is x equals 11?
That's a,
Vertical.
It's a vertical line. And this vertical line has to be going through that point. But it's x equals 11. So I can take x equals 11 and
Plug it in.
plug it in and see what the other one is. Does it matter if I plug it in the top or the bottom? No. So plug it in the top. So if x is equal to 11, you get 11 minus y is equal to 7. Therefore, negative y is equal to negative 4. And therefore, y is equal to 4. What's 11 minus 4? 7. What's 11 plus 4? 15. It is the two numbers that fit that situation. So my goal is, instead of just choosing any which y line, I'm going to choose a line that is either all in terms of x or all in terms of y. That means, I'm going to go back to my other word, I'm going to eliminate an x or a y to get a vertical or horizontal line that goes through the point of intersection. All right. So this is the elimination method. This is the one I prefer. It works much better.
so wait, your point of intersection is 11 and 4?
The coordinate, the solution is 11, 4, yeah. The point of intersection of those two lines is 11 and 4. All right. Let's make it really horrible. And then I'll show you that elimination really isn't that bad. Maybe not horrible right off the bat. 2x minus 3y is equal to 7. 4x plus 5y is equal to negative 8. I don't know. I'm just making it up. Now, unlike the first elimination example, if I add these two together, I just get another line that goes through the point of intersection. That's not going to help me, though, because it won't be nice. 6x plus 2y is equal to negative 1. I mean, it could help, but more than likely it's not. So my goal is get rid of x's or get rid of y's. So which one do you want to get rid of first? Which one looks easier to get rid of?
X.
X's are a little bit closer, 2 and 4. compared to 3 and
Five.
it's easier to make a 2 a 4. So how do I make a 2 a 4? Well,
Multiply the whole thing by 2.
and you have to multiply the entire thing by 2, both sides. You can't just do one side and ignore the other. If you multiply the left by 2, you multiply the right by 2. So that equation now becomes 4x minus 6y is equal to 14. It's the exact same line, goes through the same y-intercept and has the same slope, it's just I wrote it a little different. Now I'm going to take these two equations,
The one
and
you
if I
made.
add them together, does that help?
Yeah.
No. Because then I
You have to
get,
make one negative.
Oh.
I want one to be positive and I want the other one to be negative.
Multiply the last one or the top one, the green one, by -1.
You could, or if you were fancier, instead of multiplying by positive 2,
Negative.
negative 2. So if I multiply by negative 2, this becomes negative, this becomes positive, this becomes negative. Now things are working because when I add them together, one of my variables goes away. It gets eliminated. So 4x minus 4x is 0. 5y plus 6y is... I almost put 13y.
I said 11.
I know, I almost put 13 anyways. 11y is equal to negative 8 minus 14.
22.
I made this up and it's coming up nice.
Great.
Yeah, boring. I was hoping I'd have ugly fractions all over the place. Oh well.
That's equal.
So you're going to get y is equal
Negative.
Negative.
to negative 2. Now, once you have y is equal to negative 2, I highly suggest you go back to the two original equations, ones in green in this case, and plug y into it. Top or bottom?
Top.
Top. So we're going to take 2x minus 3, we have y, is equal to 7. Plug in negative 2. So we're going to get 2x plus 6 is equal to 7. Therefore, 2x is equal to
1.
1. Therefore, x is equal to
Yeah.
a half. So there's my fraction.
And it even, yeah.
Boring.
Fraction too.
So, y is equal to negative 2, x is equal to a half. The solution, therefore, is x is equal to a half, y is equal to negative 2, and there you are. QED. That came out a little bit better. Not that hard, right? It actually flows rather well. With the understanding that anytime we add two systems together, we get a new line that goes through the same point of intersection. That's the only backhand knowledge you need.
So,
But other than that, the system works.
So with elimination, you need a negative equation and a positive equation for it to come out right?
Well, the two I'm trying to eliminate, one has to be positive, the other one has to be negative, same coefficient, absolute coefficient. Let me make up one that's really horrible. Fractions and everything.
Let's try.
And I'll show you what I do compared to what the book would do. I think my way works better. Oh, by the way, there's so many different ways of solving linear equations, it's funny. We could do matrices.
Oh, I remember that.
Yeah, we could do matrices and go with that process, and that one actually spits out answers really quickly. Kramer's rule. There's tons and tons of fun stuff we could do. But we're only sticking to the more boring ones. So, example. A system, 5x minus 7y is equal to 13. 2x plus 3y is equal to negative 10.
Yeah, this looks like
Well, I made sure all the numbers had nothing to do with one another. They're all primed to one another, 2, 3, 5, 7. And since they're all primed to each other, I'm not going to have a nice situation like,
it. You gotta multiply both.
with my luck, my answer is going to be 1, negative 1, something really boring. Oh God, it might. That'd be funny. So, which variable do you want to get rid of? Here, the choice is irrelevant. So, pick a variable.
X.
All right, if you choose to get rid of x, I'm going to change the way I phrase this. Let's call this top one equation A. Let's call this bottom one equation B. How would you get the x's exactly the same for A and B?
Multiply the top by 2. and the bottom by 5, but make one of them negative.
Pick one.
The top one.
Okay. So you want to go negative 2 times A and add on, 5 times B. That's the process that you want to do. I like doing this because then you don't have to write a lot of stuff up here. So if I go negative 2 times A, now remember A is this line here. I have to multiply everybody by negative 2. So it would be negative 2 times 5, negative 10x. Negative 2 times negative 7,
14.
positive 14y. Negative 2 times 13,
Negative 26.
negative 26. That would be the A equation multiplied by negative 2. Then turn around and take the bottom equation, B here, and multiply by 5. So 5 times 2, positive 10x.
Plus 15.
5 times 3 is 15y. And then 5 times 10 is negative 50. So we adjusted both of the equations, so one of the variables is exactly the same, opposite sign. Then you just add them together. The x's are going to go, and you're left with 29y.
Equal negative, wait,
It's 24. It's positive 24.
Huh?
Where you get that negative 50? Oh, never mind.
Huh?
Never mind.
You were
Negative 76.
negative 76. And if you type that in your calculator, I'm really worried.
What?
2 plus 5, 7. 6 plus 0,
That's
6. And then take both sides and divide by.
29.
So your answer is negative 76 divided by 29, and trust me, it doesn't reduce. Comes out to some ugly decimal.
2.16.
You want to leave it like that.
Okay.
Because once you start rounding it, you're approximating and your answer's going to get thrown off a little bit. Now, you have a choice. I can take negative 76 29ths and shove it back into one of the original equations, but that causes horrible fractions, and then if you multiply through by the common denominator, they're huge numbers. So here's the other way of dealing with it. Over here, I have eliminated the x. Why can't I just turn around and eliminate
Why?
y? So my method is never deal with fractions at all, and go and eliminate the other variable. So if I was going to eliminate the y, what would I take and do to a?
Multiply.
By?
0.
We're concentrating on the y's here. So
gotta
you
get
multiply
above
by
3.
3, and the bottom one by,
Negative 7.
but they're already opposite signs.
So 3 and 7.
I want one to be positive, one to be negative. One's already negative, the other one's already
Positive.
positive. So I'm going to multiply the top one by 3, so 3 times a, and I'm going to add on 7 times b. Okay, so 3 times 5, that's 15x. 3 times 7, that's
Negative
21y, is equal to 3 times 13, that is 39. Ah, this marker's not working. Ah, this stinks, I have to push really hard. Yeah, so this is 3a. I hate writing lower stuff.
Well, we can let this one here.
Yeah. Woo. There we go. I just have to write really hard. Okay. Now 7b. So 7 times a 2 on the bottom, that would be 14x. 7 times a 3 would be a positive 21y. 7 times negative 10 is? And when I add these together, something interesting happens. What's 15 plus 14? 29 again. It's the same as the 29y over here.
Plus 29.
It is kind of cool what happens that the denominators of these things are going to be exactly the same. And there's reasons behind it, but it's just kind of cool to see. So it becomes 29x is equal to 31.
Yeah.
And therefore x is equal to?
Negative 31, 29.
And we didn't have to work with a fraction once. So my solution,
Negative 31 over 29.
comma,
Negative 76 over 20.
Imagine graphing this. Ooh, 29. Try graphing this. It ends up, where you have your graphing boxes. The intersection of these two lines is, someplace in there. And you would never be able to find it by graphing. So, cool way of doing it, huh? Elimination.